Okay, now that I've run through all the housekeeping items, it's time for me to introduce today's speaker. Dilip Molla is a principal consultant with EC&M Electrical Consulting Services out of Missouri City, Texas. Dilip received his BSEE degree from West Virginia Institute of Technology, and he's a longtime member of NEC Codemaking Panel 5 and is a key member of the NFPA 70E Technical Committee. During the 2012 IEEE Electrical Safety Workshop in Dallas this year, he received the IEEE Charles Proteus Steinmetz Award for his dedication to developing safer equipment and promoting safety standards to reduce the number of electrical-related accidents in the workplace. With experience designing and constructing the electrical infrastructure of petrochemical facilities while with Union Carbide from 1976 to 2001, he employed his safety by design concepts, examining each infrastructure design aspect to maximize safety, resulting in many innovations. In 2007, for his extraordinary contributions to the petrochemical industry, he received the coveted David Asbill Award, and today serves multiple IEEE Standards Association working groups related to the petrochemical industry safety and arc flash hazard analysis and recommended practices to improve electrical safety. So it's my pleasure to turn this session over to Dilip.
Thank you, everybody. My name is Dilip Molla. Some of you probably know me by now. Today I'm going to try to address the workplace electrical safety and why preventing is better than protecting. Before I get into detail, I may not be able to explain everything in a short time we have, so if you have any questions on this webinar, you have some names that may be in your area that you can call and contact them to ask specific questions. Either they'll contact us or they should be able to answer. They're all very qualified people from I-Gard. First item, anytime you have a safety issues, what are your needs? Do you need a structured approach or do you need just a haphazard approach? It's a good idea to have structured approach, and what you don't need is unscheduled process interruption. In a continuous process industry, that is a very dangerous condition. What you do need is process reliability. Unless you have some specific reason, you don't want to damage electrical equipment, because electrical equipment is lifeblood of any utility and any operation. And you don't want any unsafe work condition. You like to have safe work condition, so people who are working for you or with you are there to work safely. So how do you do that? It's very hard to remove a hazard. You have to consider risk and try to minimize or eliminate the risk. Risk is the likelihood that event will occur. Hazard is something that's potential cause harm and damage. To be truly safe, you should try to remove the hazard first, if you can, and then worry about the risk. Now, just to give you an example, most of you are familiar with ground fault circuit interrupters. They do not remove the hazard. They remove the risk. So risk, by definition, is always dependent on proper application of a protective device. There is a document, American National Standard ANSI Z10. For people in Canada, I think they call it Z10. This is a document for Occupational Health and Safety Management System. It is not a safety standard. It just tells you how to manage your safety health standards. And you can see on the screen, the scope is that defines the minimum requirements for occupational safety and health management system. Keep that in mind. NFPA 70E and all that, they define the hazard and risk reduction. Z10 will tell you how to manage it. The primary purpose of this standard is to provide a management tool to reduce the risk, how to evaluate and how to reduce that. Its application can be on any size installation, from a small company with 1 or 2 employees to a multinational company with 100,000 employees. What does NC-Z10 based on? Basically a step-by-step approach. Select a task, system or process to be analyzed. Identify the hazard. Define possible failure modes. People who are working in process industry will recognize as failure mode effect analysis, FMEA, that we normally call. Estimate the frequency, because sometimes you cannot reduce the hazard, and what is the duration of exposure. If it's a short-term exposure, the risk would be less. If it's a long-term exposure, risk will be higher. Assess the injury or illness, how severe it can be. Is it recoverable? Then determine the likelihood of occurrence. If likelihood is very low, risk is low, and you can probably analyze that do we want to do this work or not. Define the level of risk as assessment progresses. Hazard risk can be listed and ranked. Okay? And at the end, the organization selects what is your risk tolerance might be, how much risk is tolerable to you. This is a risk matrix that you will see is derived from NC-Z10, where you can quantify your hazard and your risk and see that is it catastrophic or is it a minor acceptable risk. You can see the color coding. Red is basically you do not want to take a risk. Very high. Orange is serious. High priority. Remedial action may be taken at the earliest opportunity. And medium, take remedial action next convenient opportunity. Low, risk level is acceptable. Now these are derived from NC-Z10. These definitions are just provided for illustrative purposes. And each organization has to define what is acceptable to them and what is not, depending on the hazard. In a petrochemical facility, anything that can cause ignition source may not be acceptable. In certain industries, the same risk may be acceptable. Okay. One of the main thing in electrical system, now we'll focus on electrical, before that we were talking about generic, is the impact of ground faults. This is from FM, factory mutual data, and you can see that the number of faults between industrial, commercial, and the impact. One of the hardest things for industrial facilities, especially if they are continuous process industry, is loss of production, because unless it's a batch process, you cannot start instantly. That takes a long time. So you need to avoid the best you can the ground faults. Why the ground fault is so important in electrical system? Why we emphasize the first thing is a ground fault? You'll see a picture that shows the effect of the equipment damage on ground fault. Now, anytime electrical equipment is damaged, it does not matter what industry you are in, your production is going to be affected. Whether you're IT technology or a refinery, if power is not available, something is going to be suffer. If you're unlucky, it may have injury to employees. If you're lucky, it may be limited to just equipment damage or unscheduled process interruption. Now, unscheduled process interruption may have a consequence like an environmental release. Some of you are probably familiar with that concept. What is the impact of arc flash? There are some statistics quoted, the CAP shell, run by a very qualified medical professional, Dr. Mary. They estimate the 5 to 10 arc flash explosions occur in electrical equipment every day. Most of them may or may not result in injury. National Fire Protection Association in U.S. estimates during the 5-year period 1994 through 1998, an estimated average of 16,900 reported industrial manufacturing structural fires, result in civilian deaths of 18, 556 injuries, and about $790 million in property loss. Similar data from Washington State provides the data that how many people got burned. 2000 to 2015, 350 Washington workers were hospitalized. Of these, 9% due to arc flash blast. Total workman compensation costs with these 30 claims exceeded $1.3 million. Okay? Now, workman comp is one metric. Other metric that I cannot quote, but I'm familiar with it, is civil litigation loss. They run into a lot higher than workman comp. So this is the same metrics you'll see on the arc flash. This is the advantage of Z10. You can probably put in your document where the loss should be, how it should be evaluated. If you look at the high loss, do not operate equipment. If there's a chance of somebody getting hurt, until remedial action has been taken. And that's the one thing you have to teach your people, that if there's a chance of risk, you do not want to take any risk. So on, going to serious and medium, and when you go to low, the risk level acceptable, remedial action is discretionary. That means you may have equipment loss due to flash, but you may not have people loss. All safety is depending on the primary to protect people first, then you protect the equipment. Ideally, you want to protect both. Okay? ANSI Z10 or Z10 for my Canadian friends has some activities identified, prevention and protection, and how effective they are. If you can, elimination is the best protection. If you do not have a hazard, somehow you have eliminated it, problem is solved. Next could be under prevention, you substitute with a less hazardous equipment, system, or energy. People who are used to motor control, you probably are aware that we used to use 480-volt motor control, then we shifted to 120, then we went to 24 volts, and now we are going millivolt signals. So that means we have eliminated the hazard by substituting something. Next item is engineering control, where is some process control provides you some kind of protection that you cannot go to the next step without taking some prevention steps. And engineering controls are always designed and they automatically reduce. Least effective are warnings, administrative controls, and PPE because they depend on human being reacting, doing something. Very surprisingly, industry data indicates human is prone to error 1 in 10 times. That if same operation is done 10 times, he or she can make an error 1 time out of 10, which is a very high percentage. As opposed to engineering control, a relay has a 1 in 1,000. The PLCs we use for electrical safety is 1 in 100,000. So you can see that why it is beneficial not to depend on warnings, administrative control, and PPE. I would not say not to depend totally because existing installation, that is the only choice you may have. Okay. Let's address the first item, elimination, how you can eliminate the hazard. In United States, there is an agency called OSHA, Occupational Safety and Health Act, which is 1910-333 tells you that live part to which an employee might be exposed shall be de-energized. If you are reading this slide, please keep special emphasis on the next phrase. Before the employee works or near them, and highlight the next item, unless the employer can demonstrate the responsibility to demonstrate the increased hazard or infeasibility is by employer. And that's the reason you need ANSI Z10 to put in there in your safety program. Employee cannot take on herself or himself to take that hazard by definition. Accountability is always with employer. You can delegate responsibility, you can never delegate accountability. OSHA also says the live part that operates less than 50 volts to ground need not be de-energized. But there is a condition. If there will be no increased exposure to electrical burns or explosion due to electrical arcs, 50 volts and below is not considered fatal shock, but you can still get a flash hazard. Some of you people who are used to working on the cars probably has burned screwdrivers and burned fingers. Voltage is only 12 volts. So voltage is only a measure of the current protection. Current is the one that decides what the flash protection is needed. Okay. One method to look at the system grounding. You have three kinds of grounding system that you can categorize. Ungrounded system, where your secondary side, where you're using, do not have an intentional ground. People who are sitting here, who are true electrical engineers, they will challenge me. There's nothing in the universe is ungrounded. That is true. Ungrounded here is not intentionally grounded. Every system is capacitively coupled to electrical lines. Next could be solid grounded, which is the most common use. Ideal system to use is resistance grounded, and we'll go and explain how does it benefit. Okay. Elimination of hazard, high resistance grounding. In a solid grounded system, the fault is cleared by automatic isolation and very high incident energy, controlled by Ohm's law. High resistance grounding, where we insert an intentional impedance in the circuit, it cuts down the energy and allows people to operate on the first fault and clear it when it's convenient or when it's possible. A paper that was presented at 2012 Petroleum and Chemical Industry Conference by IEEE fellow John Nelson, and he quoted, anecdotally it has been reported that 95% of faults in an industrial facility originate as face-to-ground fault. Less than 3% originate face-to-face fault, and less than 1% originate as a three-phase fault. So if you are using high resistance grounding and you maintain it properly, your probability of having an explosion is cut down by 95%. Okay? The risk. Other documents I also have mentioned. One document was EPRI, which is utility industries. 85 to 95% of faults start as face-to-ground fault. So it stands to reason, if we can eliminate the initiating condition, we won't have that problem. This practice was initiated in 1960s by industrials purely for continuation of power, that you don't want to shut down the continuous process industry. Some other documents that you might be familiar with it. IEEE Standard 141, okay, which is a red book. It tells you that high resistance grounding provides the same protection as ungrounded system. Why did industry used to use ungrounded system, delta? Mainly not to go down on the first fault. It creates environmental issues, it might concern safety issue. So red book tells you that it gives you all the advantages that you had, plus you can have some detection. IEEE Standard 242, it tells you ungrounded system offer no advantage over high resistance grounding system. The advantage you have, first fault not shutting it down in delta, ungrounded system is still available in high resistance grounding system. You can continue the operation, but one of the disadvantages in delta system is the transient voltage, which is in high resistance grounding, is removed. Okay. What happened when you happen an arc fault on a solid grounded system? Okay. A recent electrical fire caused about 400,000 damage, because when the fault happens, a tremendous arc. in a petroleum and chemical industry, and also where you have classified areas where you handle explosive gases and liquids, if solid ground system fault can initiate a fire, which is a lot worse than any electrical fault you can have. In one of the cases, one simple question was asked: was the grounding method chosen by the consulting engineer and the facility owner, operator, a contributing factor? Answer was yes. If it was a high resistance grounding system or resistance grounding system where you limit the fault current, the fire may not have happened. So when you use solid grounded system, which is very common because of the advantages of low cost, so fire and damage, if the problem happens, is not if it's going to happen, but when. Industry has experience. The industry I work with, we had experience where a motor terminal box cover blew apart. Some of you may have seen transformer throat covers coming apart. That was primarily due to solid grounded system creating so much energy during the first fault. Arcing fault on solid grounded system. Recommended practice, the Green Book, which is the premier grounding document, states that one of the reasons for limiting the current by resistant grounding may be one or the more of the following. There are 3 or 4 given. We have just shown you one to reduce the arc blast, the flash hazard. Who may have to the personnel who may have accidentally caused or who happen to be close proximity to the ground fault, which you cannot avoid. The first fault is going to happen. Electricity faults happen very quickly. Red Book, something similar says that, IEEE Standard 141. There is no arc flash hazard as there was solid grounded system, since the fault current is limited approximately to 5 amps. In Canada, I believe they limit it to 10 amps. Another benefit of high resistance grounding system is limitation of ground fault current. So equipment is repairable. Even if you decide to trip, there is no pressure, there is no requirement you continue operation. You can trip that, but the damage will be minimal. Elimination of hazard, high resistance grounding system. Like I mentioned, the concept is simple. It came in 1950s and 60s by petrochem industry. Insert a known impedance in the circuit because all the current has to go back to the source. If you limit the ground fault, you need enough ground fault current to activate your alarm system and above the charging current of your system. That way you limit that damage. Okay. How does high resistance grounding reduce arc flash? This is extracted from a book by Duncan Jacobs, the person who first time analyzed or produced a paper, the other fault, arcing fault. Up till then everybody was prone to just consider that bolted fault. All your equipment is designed to withstand bolted fault, and his opinion was, he worked for a very large company which was leader in electrical industry, manufacturers. 95% of all electrical faults are face to ground faults. They start as face to ground. Then they escalate to face to face. So it stands to reason, if we can prevent them from escalating, we can never prevent the first fault from happening. There could be a cable insulation damage, motor damage, but yes, we can prevent the second fault to not allow it to go to face to face. This is a schematic you see on your screen. Basic electricity requires that all the fault current has to go back to its source, which is the transformer neutral. And you see some arrows that tells you that how it is returning to the source. Now you can see how the protection is achieved. High resistance grounding, what do? We insert a known impedance there. Once you insert a known impedance, you're limiting the ground fault to whatever you decide is prudent for your system. Now, how does it help? thermal damage is based on I squared T. The current is flowing for a time, square root of that, multiplied by the T, that's the time it takes to clear a fault. So if you have a system grounding, solid grounding, and just for discussion's sake, you have 22,800 ground fault, as opposed to you limiting it to 5 amps ground fault by high resistance grounding. So if you compare that, the damage potential has been reduced by over 20 million times. That means on a high resistance grounding, you probably would not have any damage. On solid grounded system, you will have a fire, you'll have a big explosion, and you have a potential of incidental process fire or person getting hurt. So how do you eliminate that, and how would you detect that? Is ground fault location. One of the things that Delta cannot do is how to detect a fault. In this case, you have a contactor or some solid-state device that is giving you time 40 to 60 times a second. It opens and closes. So all you need is to where that arcing current is flowing. Once you can do that, you're able to detect and isolate. If it's a quick fault, you can activate in 15 minutes or so and try to isolate the fault. Now, newer systems have solid-state devices available. They'll automatically do work for you. Okay? If you see how it works, 40 to 60 times a second system will pulse. So you don't need actual quantity measurement. If you have a clamp-on meter around it, you will see it will go back and forth 40 to 60 times a second. When you reach the fault point, it will go steady so you know where the fault is. So it's a very simple system to detect ground faults. Okay? Now what if the grounding resistor opens up? Then you have a backup sensing resistor that you can have that can give you an alarm that a main resistor is opened up or is not working, so you can plan your outage and avoid an unplanned outage best you can. High resistance grounding depends on isolation of first fault, because the first fault is going to be whatever your resistance limits. What if you have a second fault? Second fault will go phase to phase. So if the second fault happens, before you can isolate the first fault, you will have a phase-to-phase fault with very high energy. Now technology is available that you can monitor all your feeders and you can assign priority to them. For example, if you have a lube oil pump that is supporting a large motor generator, you can assign the highest priority. If a second fault comes, which is of lower priority, it will be automatically tripped. So you'll never have two faults at the same time. If the third fault comes in, it will be treated as a second fault. So priority-wise, the lower priority system will trip, giving you extra advantage. That is very important because some equipment you may not want to lose till its end, till the process shuts down. Okay. Next item is substitution. What is the technology to substitute with less hazardous or less risky environment condition? You will see a chart on your screen that what happens by reduction of time. If you can clear the fault in 35 milliseconds, which is about 2 cycles, your incident energy based on 40 kA voltage fault at 18 inches working distance is about 2.9, as compared to if it clears in 3 times 100 milliseconds, which is roughly 6 cycles. You'll see the fault has gone up to 8.31. If it clears in 500 milliseconds, which is close to 30 cycles, you can see now you have 42.8 some calories. Now, I'm sure you can see by the numbers, if a fault happens and your job is to protect your people, which one you rather them be exposed to? 2.9 or 41.5? That's your decision. This is a chart produced by Dr. Land, who did a lot of research on equipment damage. You see two lines, red and green, and you can see how many points for research he tested. If the incident energy or the heat is below the green line, equipment is probably repairable. If it's above the red line, it's probably not. You'll have a major damage. So in design stage, you want to keep everything below that green line if you can. What if it's in the middle? Now it is it depends condition. What was the equipment? How much was the damage? Is it repairable? Is the process interruption happens? Some of the devices are available to limit the fault current or limit the time. Arc flash is proportional to current and clearing time. So reducing either one can reduce your incident energy or the flash. On limiting the fault current, let-through current is current limiting fuses or breakers. They operate very quickly. Thereby, let-through current is minimized and equipment and flash is limited. Equipment damage and flash is limited. On limiting the time, you have zone selective interlocking relays, which have come recently. You can have arc pressure sensors and light detection relays. We'll try to address each one of them quickly. First is current limiting fuses and circuit breakers. National Electrical Code defines them for protection of the equipment or high available short circuit current condition. So it is going to limit the let-through. Now you cannot use a fuse to protect a breaker, for example, unless they have been tested together, because downstream device has to be passive device. Okay? They are able to protect the equipment because let-through current is less. If the let-through current is less, I squared T, the current squared, and clearing time is less. That then limits the damage to that equipment or incident energy of the flash. These are some of the examples. If you see that, okay? If you have, for example, a non-current limiting fuse, what you see that in first slide. At 47 inch, you have 5.8 calorie. If you calculate that at 18, you will have close to about 20 to 25. It's exponential. Now, when you have a current limiting fuse, if they operate in current limiting range, you have 22 inch, about 1.6 calorie. If you have a 30 amp fuse, you're looking at only less than 0.25 calorie, 18 inch working distance. So basically, current limiting fuses and breakers, if they operate within the current limiting range, reduce the let-through current, reduce the energy, reduce the damage. I mentioned that they reduce the energy. You can see that if it's a non-current limiting fuse, you see the test 4 on the top. You can see the colored area denotes how much energy was. If you can count, you'll notice it's about close to 6 cycles or so before it interrupts. Test 3, it interrupts in half cycle or less. Test 1, it interrupted even quicker. Now, UL defines a current limiting device can only be classified as current limiting if the clearing time is half cycle or less, because it reaches the peak at that time. Most of the devices will clear faster than that. What are the other options? Limit the time. Zone selective interlocking, arc pressure relay, okay, and optical detection. This is a traditional system where we coordinate and try to protect the process Coordination main principle is the device closer to the fault should operate first. If the downstream devices do not have ground fault protection, you're depending on the main breaker with a delay to act as a backup. You can see 1 second is an eternity in electrical. It is 60 cycles. We talk in cycles. In US is 60, in Europe is 50 cycles, 50 hertz. So conventional coordination, how do we do that? Normally all of you are probably familiar with it, something that we increase the magnitude and try to increase the time delay. So if the fault is downstream of the breaker, the lowest breaker you see, which is set at 10 amp 0.25 seconds, that will operate first. If that does not operate, next is set at 20 amp 0.6 seconds, that will operate, and so on. At the end you have protection of resistor. You can notice this set at 1 second. So it's a very high setting. If you calculate incident energy on these 1.25 seconds is 15 cycles, is going to be pretty high. 15 cycles is a big time. You can do zone selective interlocking. Since it's very hard to coordinate all instantaneous, zone selective was the concept introduced by a very good manufacturer. That means they talk to each other. If the fault is downstream, that relay or protection device is telling the upstream one, I have it. You don't have to worry about it. If the fault is upstream of the lowest device, lower device does not see, so upstream device will quickly trip. Only disadvantage of this is it's very hard to retrofit unless you have the foresight to buy equipment that's conducive to zone selective interlocking. This eliminates the additional delay for coordination purposes. Every breaker is set at quickly operation if it is in their range. Same kind of zone selective you can do with current limiting fuses. Of course, that fuse manufacturer will tell you what minimum rating or coordination rating should be. Some may be 4 to 1, 6 to 1, and so on. So if you're using current limiting fuses or other fuses and you want to coordinate, I suggest you talk to the manufacturer that what is the coordination ratio for that fuse might be. Optical detectors and zone selective interlocking, again, that you can do that by your relays also. Of course, now you're depending on time-based. You can see that time goes up or setting goes up. As opposed to zone selective, but when you talk to each other, interlinked, it protects automatically. The fastest device you can get is optical. Whenever there is an arc flash, it is accompanied by sound and light. Sound travels at 340 meters per second. Light travels 300 million meters per second. So the first thing you'll always see in the flash is the light, then you see the sound. And that technology is very effectively being employed by manufacturers to reduce that incident energy, cut down the time. Basically, thrust of all the zone selective interlocking and optical detection or current limiting fuses cut down the opening time. So what is the difference between high resistance grounding and optical detectors? Basically, you need to, one prevents accidents, one acts after that. And this is another picture of optical detection that you see how fast it can operate. Okay. Internal pressure will build up, so sound will pick up. Some of the technology available, pressure sensors, which is a slow process, or light arc detectors, very fast process. Optical or pressure sensors work that whenever the explosion happens, there will be some light or pressure that activates the breakers or an interrupting device. Now, just to make sure that a air brake might activate essentially on every time it operates. So you series that with other device. with a current or something, that means two conditions have to be satisfied, the trip happens. The same second thing when you have that second condition is slows things down. So this but assure that you won't have any false tripping. That sentry device you see, that's made by I-Gard, that has the optical detection input built in, and then you have a display center. Same thing you see, that layout of optical or pressure sensor. You have a trip unit that can basically accommodate multiple devices, the current unit input or pressure sensor input. And that way you can have an AND gate to prevent the false tripping and cut down the requirement for incident energy. You see a picture there that how does it work, that you basically have a zero sequence CT, that you see that on your slide, that inputs to a relay. It can detect pressure also as a backup or light, and you're cutting down the time that is required for tripping. This is a new concept being introduced. Right now, the tripping time, it does not matter how fast you can isolate it, how fast you can detect it. Breaker takes 3 to 5 cycles to trip, because breaker is an electromechanical device. If you could have a solid-state device, which is the Optima system, basically is a solid-state device that doesn't need that kind of delay, it can trip in 1 millisecond, about 9 milliseconds total. 1 millisecond detection time and 8 milliseconds for operation. It is available, as I understand, in the industry about 2000 amp and 50K at 480 volt. Now you can see the comparison. If you're tripping with an overcurrent relay, your clearing time is 2 seconds. Your incident energy is going to be about 211 calorie per centimeter squared. If you're tripping by instantaneous, you lose the coordination, you're back to 47. If you use just optical detection, you still need to give the breaker tripping time. It's about 9 calorie per centimeter squared. If you can see the solid-state breaker, which total clearing time is about 9 milliseconds, 8 milliseconds for operation and 1 millisecond for testing, you can cut down to 1 calorie per centimeter. I don't need to explain which one is better for safety. Lower the number, better off you are. Next technology, engineering controls, where some operation has to be done to eliminate the hazard. Some of the technology is available. Remove person from the hazard. From all the investigation I have done for arc/incident burn injuries, I have never seen a person who got hurt who was not there. So first thing you have to do is get them out if you can. They are not there, they cannot have. When you're doing close type transitioning, short time there is a very high current and you can have interruption and incident energy. Avoid hazard of flying doors and shrapnel. PP does not protect you against shrapnel. Two types available. You can have permanently installed or portable that you can use as you need them. You can do remote switching. Permanently mounted mimic panels from the control room. Advantages is they are permanently mounted. They can be operated through mimic panels or SCADA system. Disadvantages, it takes some wiring, takes some equipment, so they're expensive to install. There is increased chance of operating the wrong breaker because you're operating from the remote location, and a wrong operation of breaker may create a safety hazard. It may need some cabinet or wall space for even the SCADA system, I/O racks, input-output racks. You can use a remote actuator, which is magnetically coupled to that device, and you go 20 feet or 25 feet, which comes in different length. You can operate from remotely. Distance is your friend on arc flash. Further you go, better off you are. Disadvantage of this system might be they're not permanent installed, so they depend on human to operate that, human to install that and do that. If you're interested in your safety, you'll probably train your people to do that. Okay? You can remote rack it. Most of the accidents happen whenever electricity changes state. Remote racking device can be installed to do it from a remote location. Okay? You can install infrared windows. They can prevent incipient fall, that you can do that, as opposed to opening the doors. So you can see there are a lot of safety precautions available that you can consider. You can use arc-resistant switchgear that protects the people from the front. It is only for human protection. It may destroy the equipment. NCC 3720.7 is a testing standard. That means somebody from the front will be protected if the equipment is properly designed. Now you can have a total system protection. That will cover everything. That means you can have arc-resistant switchgear that will protect the people but doesn't protect the equipment. You can have high-resistor grounding with second fault protection, so you will not have a second fault. You can put a pressure sensor to the circuit or light sensor to a circuit. So just to recap, you also have another option of warning. The fourth method. Warnings are the least effective. It depends on people to listen. Automatic or manual, permanent or temporary. Anything that depends on human has a higher chance of failure. Okay. Then you have PPE, administrative controls. Don't do this thing. PPE should be the last protection. For people who do know, PPE is only designed to protect onset of a second-degree burn. And if that rating of the equipment is only effective 50% of the time, do you really want to take a chance getting a first-degree burn, which is also very painful? Okay. So this is a total recap. Which system works for you? Do something. Don't ignore it. All the way from elimination to personal protective equipment. Your structured approach. You need to have a plan. If you fail to plan, you plan to fail. Ideal is prevented by using the equipment that will prevent the fault from happening. That is the primary difference between high-resistance grounding and other protection like zone-selected interlocking or PPE. They only act after the fault happens. High-resistance grounding with second fault will probably minimize the risk of fault happening. And you all will agree with me that prevention is always better than protection, even though protection is sometimes needed. So this is what you started with, what you don't need and what you do need. You don't need unscheduled process interruptions. You want to shut down when you need it. You want process reliability. Okay? You don't want to damage electrical equipment that cannot be repaired. You want the equipment to function. You don't want unsafe work conditions to affect the morale and injury. You protect safe work conditions. Okay? If you have any questions, this was the first slide on this webinar because I went at a very rapid speed for you, which I don't think that I could explain everything in there. Please contact one of these people and they'll be glad to answer any of your questions. They're all very qualified. They all know the system. You see this on the names on the screen. Okay. Thank you very much.
Great. Thank you, Dilip, for a very informative presentation. Before we jump into our Q&A session, I'd just like to take a moment to ask you, the audience members, to answer the feedback form that's going to appear on your screen now. If you have pop-up blocker technology enabled on your computer, we ask that you disable it for a moment so that you can receive the form and fill out and give us some feedback on how things went today. And with that, I will jump into the question session here. We've got about 9 minutes, so we'll be able to offer up some and have Dilip answer as many as we can work through. Dilip, the first one is high-resistance grounding really cost-effective on a 240-volt system?
It depends on what system it's for. It's not the voltage, it's the intent. If your need is to protect from undesired operation interruptions, yes, it is. We use that in industry, especially when we give 120, 240 volt to inverter power supply. So you have to analyze when it's effective. 240 volt can also cause a lot of injuries. So the voltage is not the determining factor. It is your need for safety and process continuity.
Good points to keep in mind. Okay, how much of this helps if OSHA doesn't allow you to work on energized equipment? I guess somebody's feeling like, OSHA's saying to us, don't do anything energized, so they're wondering how this is going to really help.
Okay, OSHA 1910-333A1, what I had shown on the screen, it says where the employer can demonstrate the shutting down power will have increased hazard or infeasible. All this helps a lot in your risk analysis. If you can convince yourself and convince the management that, hey, system is okay, if the first fault happens, which is 90 to 95% of the time, we are limited to 5 amps or less. What is the probability of second fault happening, which we are doing that? So OSHA does not restrict blanketly. OSHA wants employer to demonstrate that is necessary and it can be done safely. So high-resistance grounding is a very effective tool to reduce the risk.
Okay, great. I got to go back to the survey for 1 second here, Dilip. If you could please click on the red survey widget at the bottom of your screen to take the exit survey. That's how you can get to put your comments in. Okay, so back to the questions. One of them has to do with, I've got a person says, I have a 277-volt lighting system. How do I take advantage of a high-resistance grounded system in that situation?
Okay, this is a very common question because looks like in 60s and 70s design was done that you have a very large transformer solidly grounded and you try to use lighting from one phase 277. Now you can very easily put a smaller transformer just for lighting. An advantage it comes is tremendous. A typical 2 MVA transformer, 2000 kVA transformer, if it's work for lighting, you have close to 40,000 amp voltage fault current. If your lighting load is only 100 kVA and you use that, you'll cut it down to about, 5,000 amp or something like that. So it is very cost effective to isolate the single phase load and protect your people by design. If you have 277 volt lighting, I will very strongly advise you to consider isolating lighting system with a smaller transformer. Just for your information, 277 volts is the major cause of burn injuries as well as shock injuries. So please look at your system and use a smaller transformer if you can.
Great suggestion. Okay, this has to do with a person that's dealing with a 480 volt delta ungrounded secondary. Says they have no ground fault detectors. How can we make this type of system safer?
Okay. There is technology available to install a zigzag grounding transformer on the secondary and derive a ground detection system. So it is right now, technology is available. If you call one of those 4 names or 5 names we have shown you, they'll be glad to assist you. That is a very common because all 1950s and 60s installation was done delta-delta. You can derive a artificial neutral and have the same advantage as high-resistance grounding.
Okay, here's a question. You mentioned 3 to 5 cycle opening for breakers. This fast opening is required to limit the arc flash with some of the controls. What is the industry doing to ensure the breakers are in proper working condition to ensure that they actually respond in this type of time frame?
Okay, my compliments to somebody who asked that question, and thanks. It is all this technology, all the NFPS 70E and all the technology is based on equipment is properly installed and maintained. Whether it's a 3-cycle breaker or 5-cycle breaker, that is based on the equipment was properly installed and maintained. If equipment is not properly installed and maintained, no time can be calculated. We do not have any technology to say if you don't maintain the equipment, what the clearing time is going to be. Since the shock hazard effect and the flash hazard both depend on how fast the clearing time should be, so equipment should be properly installed and maintained. Again, my thanks for somebody who asked this question.
Yeah, that's definitely a problem that needs to be addressed for sure. Okay, can the system and equipment BIL be exceeded when applying HRG?
Absolutely not. Equipment rating and BIL, or basic impulse level, is based on lightning protection. All HRG will do, if you have a face-to-ground fault, it'll isolate. So no, equipment cannot exceed its rating under any circumstances.
Okay, great point. Let's see here. We've got this person's asking about a room that's occupied with motor control centers. And do these rooms provide some type of arc flash hazard, I guess is the question they're trying to ask.
Yeah, I think somebody is trying to take advantage of me being member of 70E. Answer it depends. If the equipment is properly installed and maintained, risk is minimal. If equipment is not properly installed and maintained, I cannot quantify that. So people have to analyze their own condition, and I think I have a very good guess who will ask that question. So it's no definite answer. It depends on how good your equipment is maintained, how much you think it'll operate in time. So risk is minimized, not the hazard.
Okay. How can the Red Book state that resistance grounding eliminates an arc flash? I believe it reduces the probability for an arcing fault, especially on the first ground fault. But if a second ground fault were to occur, the energy is present for an arc flash.
That is absolutely correct. I'm also a member of Red Book. Red Book theory is based on that when the first fault happens, maintenance people will take action to remove that before the second fault happens. If that theory is accepted, Red Book is correct. If the fault is not removed and the second fault happens, the person who is asking question, I mentioned that went to face-to-face. That's the way that I was recommending, have the newer technology which automatically isolates the second fault. So you're absolutely correct. It does not eliminate totally. It reduces the risk. 70 is going to risk evaluation as opposed to hazard evaluation.
All right. Here's a question on high-resistance grounding in commercial buildings. The person's question is, they say high-resistance grounding is not recommended in commercial buildings. If this is correct, why is that the case?
There is no such restriction. It cannot be used in commercial buildings. If you look at the National Electrical Code, if the person is from United States, 25036, will tell you it can be used. In fact, in last cycle, we intentionally had commercial buildings in mind, so there is no restriction at all for not allowing it in commercial buildings.
All right. I think we've kind of hit our hour-long mark here, so we're going to cut it off there. I just want to... On behalf of EC&M, I'd like to thank I-Gard for making today's webinar possible. I'd also like to thank Dilip for an outstanding presentation today and great answers on those questions that were submitted. As for our audience members, we really look forward to hosting you all at a future EC&M event, so enjoy the remainder of the day, everyone. Thanks.